Let's now proceed to the dot product or the scalar product. So what is a dot product or a scalar product of two vectors? Let us try to consider now that the two vectors are now your vector A and the other one is now your vector B. And the included angle between the two vectors is equal to theta. Now, so the dot product of two vectors A and B. So we now have the dot product dot B of two vectors is equal to the product of the magnitudes of the two vectors by the cosine of their included angle. We have the magnitude of vector A. Okay, so this is the magnitude of vector A. And we now have the magnitude of vector B by the cosine of their included angle. Now, the result of the dot product of two vectors is a scalar. So that is a scalar. Now, you try to take note in here now that your theta in here should be greater or equal. Your theta should be greater or equal to 0 but less than 180 degrees. That is less than 180 degrees. Now, if theta, okay, if theta is, if theta is greater or equal to 0 but less than 90 degrees, now the scalar is, so you have the scalar is positive. So which means to say that when theta is greater or equal to 0, less than 90 degrees, the angle theta is an acute angle. So that one is an acute angle. Now, if theta is greater or greater than 90 degrees and less than 180 degrees, then the scalar is negative, which means the included angle is an obtuse angle. So that is an obtuse angle. Now, if theta is equal to 90 degrees, now this means to say that the two vectors are perpendicular. So the two vectors are perpendicular. So if you go back to the definition of the dot product of two intersecting vectors, it is equal to the product of their magnitudes by the cosine of their included angle. The included angle is 90 degrees, hence the cosine of 90 degrees is equal to 0. So in here, the scalar is equal to, so we have now the scalar is 0. One use of the dot product is to obtain the rectangular component of one vector along any direction. So the rectangular component of one vector along any direction. Now, let us try to determine the component of the vector A in the direction of the vector B. And let us try to consider that component in there is now, okay, so this is 90 degrees. So the component of the vector A in the direction of B. Let us consider this one as the magnitude of A in the direction of point B. Now, from the definition of the dot product, so we have A dot B is now equal to the magnitude of A times the magnitude of B by the cosine of the included angle. So if you're going to get now A cosine of the included angle is now equal to the dot product of vector A dot and vector B all over the magnitude of B. So in other words, this is equal to the vector A dot vector B all over the magnitude of B. So that is A cosine of theta. Now, you try to take note that from this figure, cosine of theta is A all over. Cosine of theta is equal to AB all over A. So, from this figure, you try to take note, cosine of theta is now equal to A, that is B all over the magnitude of the vector A, all over the magnitude of the vector A. So in other words, your A cosine of theta is now equal to AB. So you try to look at the figure. So in this figure, your AB is the component of the vector A in the direction of point B. So we have now your component of the vector A in the direction of B is now equal to the vector A dot vector B all over the magnitude of vector B. Now, you try to recall what is a unit vector. So, a unit vector is equal to the vector itself divided by the magnitude of that vector. So, if B is the vector and your B in here is the magnitude of vector B, hence this is a unit vector B. So in other words, the component of, so this is the component of the vector A in the direction of B is now equal to the vector A dot a unit vector in the direction of B. So, the dot product is therefore useful in determining the component of a vector in any desired direction. What are the properties of the dot product? So, the dot product of two vectors is commutative, which means to say that vector A dot vector B is equal to vector B dot vector A. Another property of the dot product is associative when multiplied by a scalar. So we have m is a scalar, and we now have the vector A dot. N is also a scalar. Okay, multiply this one by vector B. So, this is associative when multiplied by scalar. So, this is equal to mn vector A dot vector B. Another property of the dot product is distributive over vector addition. We have A dot vector B plus vector C is now equal to. So this is distributive over vector addition. So our vector addition in here is vector V plus vector C. And therefore, this is A dot vector A dot vector B plus vector A dot vector C. So that is distributive over vector, the dot product of the orthogonal unit vectors. So the orthogonal unit vectors again are directed in the positive x, y, and z axis. So in the positive x-axis, that unit vector is equal to I. And the positive y-axis, the unit vector is equal to j. And the unit vector in the z-axis, orthogonal unit vector in the z-axis, is now equal to k. So, the dot product of the orthogonal unit vectors, so if you have I dot I, this is equal to the product of their magnitude. So, the magnitude of a unit vector is equal to 1 times 1 multiply this one by cosine of 0 degrees. So you try to take note that the included angle is equal to 0. And cosine of 0 is equal to 1. So similarly, if you are going to get j dot j is equal to, so these are unit vectors. So the magnitude is 1 by 1 times the cosine of their included angle, and the included angle again is equal to 0, and that one is equal to 1. And your k dot k is now equal to 1 times 1 by the cosine of their included angle, which is equal to 0, and cosine of 0 is equal to 1. Now, let's try to get now the dot product of I dot j is now equal to 1 times 1 cosine of the included angle, and the included angle in here is equal to 90 degrees. And the cosine of 90 degrees is equal to 0. Okay, which is the same as j dot I. So, from the first property of the dot product, the dot product is commutative. So, I dot j is equal to j dot I. We now have j dot k. So, j dot k is equal to 1 times 1 cosine of the included angle, and that one is equal to 0, which is equal to k dot j. So it is again commutative property. And we now have your k dot I. So k dot I is equal to the product of their magnitudes 1 by 1 by the cosine of their included angle, and the included angle is 90 degrees, that is equal to 0. From the commutative property of the dot product, that is also equal to I dot k. How are we going to evaluate the dot product of two vectors? Let us try to consider vector A. So this is now your vector A. And your vector A is AX I plus AY J plus AZ K. Another vector is now your vector B, which is equal to BXI plus BYJ plus BZK. So vector A dot vector B is now equal to AXI plus AYJ plus AZK. Dot vector B, which says BXI plus your BYJ plus your BZK. So the dot product of these two vectors, therefore, is now equal to, okay, let's proceed now. Let's try to recall the properties of the dot one of the property of the dot product. It is associative when multiplied by a scalar. Okay, so AX in here and BX are scalar. So we now have AX, there's now your BX, we now have I dot I. AX and BY are both scalar. So plus your AX, we have BY, so that is I dot J. I dot J. Plus, we have AX, BZ, I dot K. And then we have plus AY and BX again are scalar. So we have AY, BX, that is J dot I. That is J dot I. Plus, we have your AY, J plus BYJ plus, okay, so your AY and BY, so we have our scalar values. We now have J dot J, so that is J dot J. Plus, we have AY and we have BZ, both are scalar, so that is now your BZ. We have J dot K, so J dot K. Plus, AZ and BX are both scalar. AZ, BX, K dot I. K dot I. Plus, we have AZ and BY, again, are both scalar. So we have k dot j. So that is k dot j. And then we have plus az, and your bz in here are again both scalar. We now have k dot k. Now, from the orthogonal unit vectors, this is your x, so we have your I. This is your y, so we have your j. And this is now your z axis, and that one is now your k. So from the properties of the unit vectors, I dot I is equal to 1. And therefore, this is equal to 1. So this becomes ax bx. I dot j is equal to 0. I dot k is also equal to 0. J dot I is also equal to 0. Okay, j dot j is equal to 1. So that is plus ay by. J dot k is equal to 0. K dot I is equal to 0. And k dot j is also equal to 0. So k dot k is equal to 1. So that is plus a z b z. So that is therefore how to evaluate the dot product of two vectors. Now, you try to notice in here now that the dot product of two vectors in here, the result is a scalar. Because your ax, bx, ay, by, and az, bz are all scalars. So in other words, the dot product of two vectors is equal to the sum of the products of their respective rectangular components. So this is equal to the sum of the product of their respective rectangular components. So the rectangular component of A in the x direction is ax, B in the x direction is bx, plus the rectangular component of A in the y direction is ay, and B is by, and the rectangular component of the vector A in the z direction is az, and for vector B, that is equal to bz. So that is how we have to evaluate the dot product of two vectors. So it is the sum of the products of their respective rectangular components. Sample problem number 1. Find the component of the first A, the component of the first A which is equal to 5i plus 2j minus 3k. That is parallel. So that is parallel to vector B equal to 4i minus 4i plus 3k. So the x component of vector A is 5, the y component is 2, and the z component is minus 3. that is parallel to B. And the x component of the vector B is minus 4. Now the j component is equal to 0. That's why you cannot see any j in this vector. And the z component in the z-axis of vector B is equal to 3. So let's try to determine the component of A. So this is now the component of A. So this is the component of A in the direction of B. Now, if you try to recall again that one use of the dot product is to determine the rectangular component of a vector in any desired direction. So at this time, let us try to determine the component of vector A parallel to vector B. Hence, the component of vector A in the direction of B, so is parallel to B, in the direction of B is now equal to that vector, and that vector is now your vector A dot a unit vector in the desired direction. And the direction is in the direction of B. So how are we going to determine again the unit vector? So your unit vector B is now equal to the vector B divided by the magnitude of that vector. And the magnitude of that vector is now equal to the square root of the x component square plus the j component square plus the y component square plus the z component square. So the x component is negative 4. If you square that, it will become positive. So 4 square. Now 0, the y component is equal to 0. And the z component is 3. So that is 3 square. And therefore, this one in here is equal to the square root of 4 square plus 3 square. So let's try to substitute this value in here now. That your n, b, the unit vector in the direction of b, is now your vector b. So that is minus 4i plus 3k all over the magnitude, and that is now the square root of 4 square plus 3 square. Hence, the component of the vector A parallel to B is therefore equal to the vector A, which is 5i plus, that is 2j minus 3k. Now, that a unit vector. So we have the unit vector. So we have your vector B is minus 4i plus 3k all over the square root of 4 square plus 3 square. The component of the vector A in the direction of B is therefore equal to, okay, so we have 5 times negative 4. Okay, so the dot product of two vectors is the sum, okay, of their respective rectangular components. So it is 5 times negative 4. So that is AX, and the other one is BX in our previous discussion. So we have 5 times 4 is negative 20. Okay, plus 2, we do not have J in there, so 2 times 0, so it's equal to 0. Okay, plus negative 3 times 3 is negative 9. So let's try to divide this one by the square root of 4 square plus 3 square. And this is equal to minus 29 all over the square root of 4 square plus 3 square. And this is equal to negative 5.8 kilonewtons. 5.8 kilonewtons. So you try to look at now the result of the dot product. It is a scalar. Now this negative sign in here indicates that the component of A along B is opposite to the direction of B. So it is opposite to the direction of B. So that is the component of A in the direction of B. There's your sample problem number 2. Resolve vector A, which is equal to 6i minus 4j plus 5k in kilonewtons into 2 vector components. One parallel to B and the other perpendicular to B. So your vector B is 4i plus 2k. So let's start determining the component of A parallel to B. So the component of A, so we now have component of the vector A parallel to B. We have the component of vector A parallel to B has been denoted as AT. And this is therefore equal to the vector A dot a unit vector in the direction of B. So the definition of a unit vector in the direction of B is equal to the vector B all over the magnitude of that vector. All over the magnitude of that vector. So your vector B is 4i plus 2k. So the magnitude is now equal to the square root of 4 square plus 2 square. It's 4 square plus 2 square. So that the component of the vector A parallel to B is now equal to the vector A, which is 6i minus 4j plus 5k. That a unit vector B. So we have that 4i plus 2k all over the magnitude of that B, and that is the square root of 20. So again, let us try to evaluate the dot product. So 6 by 4 is 24. Again, j is equal to 0, 4 times 0. And then we have 5 by 2 is 10 all over the square root of 20. So this is therefore equal to 34 all over the square root of 20. And this is equal to 7.603. 7.603 kilonewtons. Now, let us try to express this component of vector A in the direction of D in its standard Cartesian form of representing a vector. Standard Cartesian form of representing a vector. We now have your vector AT. So your vector AT. So we're now going to express this in its Cartesian vector form as now equal to the magnitude of this vector, and the magnitude of that vector is equal to AT. So if you're going to multiply this one, this AT by a unit vector. Okay, so by a unit vector, and that is now your D. So this is therefore equal to, so we have 7.603 kilonewton, and that unit okay, so that unit vector is now direction of B, so that unit vector is equal to, so we have this one, multiply this one by, we have 4i plus 2k over the square root of 20. And this is therefore equal to 7.603 by 4, divide this by the square root of 20. This is 6.797i. So this is equal to 7.603 multiply this one by 4 all over the square root of 20 plus 7.603 multiply this by 2 all over the square root of 20. Okay, so this is therefore equal to 6.797i plus 3.399k. So this is in kilonewton. So that is now standard Cartesian vector form of the component of vector A parallel to B. Let's now then determine the component of A perpendicular to B. Okay, so if this is your vector A, which is 6i minus 4j plus 5k. So the component of A parallel to B is denoted as 80, and this is equal to 6.797i plus 3.399k. Now, take note that this component is parallel to B. Now, the component parallel to perpendicular to A is also the component perpendicular to the component of A parallel to B. So let us try to consider that this one in here is now your AN. That is perpendicular to B. Now, you try to take note in here now that a vector is represented by its components. Okay, since we have the components of vector A parallel to B and the components of vector A perpendicular to B. So, it makes an angle of 90 degrees. So, this is represented by. So, we now have your AT plus vector AT plus vector AN. Okay, plus vector AN. So we now have vector AN is now equal to the vector A minus the vector AT, or the component of that vector parallel to B. So this is therefore equal to the vector A, 6i minus 4j plus 5k minus, that is minus AT. So we have 6.797i plus 3.399k. And this is therefore equal to 6 minus 6.799 is 0.797i. So we do not have j again in there. So we have 5 minus 3.399. So 5 minus 5, this is, so we have, so this is equal to, so we have 6 minus 6.797 is negative 0.797i. Okay. So, minus 4j, so we do not have j. So, we have minus 4j. So, I'm just going to do it in this manner. Okay, so we have 6 minus 6.797i. And then, plus, we have minus 4. Okay, so plus, okay, minus 4 minus 0. We now have your j. So we have plus 5 okay, minus 3.999. Now, if you try to take a look at this point, that when you're subtracting a vector, now, so the sign will change. And this is therefore equal to 5, okay. Okay, the component perpendicular to AN, 6 minus 6.797 then minus 4, okay, so minus 0, and then we now have 5 minus 3.399, and that is now your k. So this is equal to 0.797i minus 4j. We now have plus, okay, plus 5 minus 3.399. So this is 1.601k. So this is therefore the components of the vector A perpendicular to